Right, so I'd like to thank Manish for organizing the conference. I'd like to thank him personally. And I would also like to thank the entire travel team who's done a fantastic job. I just met them yesterday. So if I mess up the names, then excuse me. Dikshita, Amay, and Saurav, and I was a little confused. Is it Krishna Gopal or Gopal Krishna? And right, so then Rahul made an observation that it's KGB, and I said, okay, I got it, okay? Right, so this is joint work with Ajit Diwan at IIT Bombay and Michael Plantholt, basically. These are the two main authors. Mike Plantholt was my colleague for 30 years at Illinois State University. The other two, Justine and David, were undergraduates at Illinois State University. So over there we have a tradition of including undergraduates in our research, trying to have them at least see the process and maybe contribute a little, right? You know, the contributions end up being small most of the time, but you know, at least they can work on some cases and see how mathematics research is done. And right, so those are the two students involved in this thing. The whole thing is based on about 2 or 3 papers and one which has not been written yet, okay? So what happened is I retired 3 years ago, and there was some stuff that Mike and me and some others were working on, and I said, Mike, I'll do the writing, I'm retiring now, yeah, okay? And 2 years passed by, I did nothing after I retired. And last year, Sunitha called me to give a talk at a workshop that was held. And I said, okay, I'll give a talk about this and then I'll get back into writing it. So I gave a talk and then I did some writing for 1 week and did nothing for 1 year. And then now Manish said, would you come and give a talk? I said, okay, you know, let me give basically the same talk, and then after I go home tomorrow, I will write up some more stuff, and hopefully it will last longer than 1 week now. Okay, so here we go. Hey, by the way, we could have just called this entire session graph decomposition, except for the first talk, it seems. So anyway, a graph H is set to decompose a graph G if you can break up G into isomorphic copies of H, okay? So for example, on the left is H, which has been called P4, the path on 4 vertices, and on the right is G, and you can see a H decomposition of G. So I've broken G into 3 copies of H, yes? The red one, the blue one, and the black one. By the way, those are the only 3 colors I can see, okay? So yes, so I'm colorblind, and everything will be either red, blue, or black. Okay, that's all I can see. So nothing with chromatic number index bigger than 3. So, okay, so the general graph decomposition problem, of course, is you fix the H. Okay, H is fixed, and G can have variable number of vertices, and you say, does H decompose G? Okay, that's the computational question. Okay, Dorr and Tarsi said graph decomposition is NP complete if some component of H has at least three edges, yes? So, by the way, the H doesn't have to be connected, right? You know, you could say, here's my entire H, and would you decompose the given graph G into pieces like that, yeah? Okay, so what they said is if your graph H has at least 3 edges, then the problem is NP complete, okay? So in particular, if you wanted to decompose a given graph G into paths of length 3, it's NP complete, yeah? Okay, so there's virtually no hope of finding anything really nice in general there. That's what it says. Okay, now here's the thing that, yes?
or this or this. So, I mean, not necessarily uniform decomposition, multi-decomposition, whatever. That must also be anti-complete.
Yeah, so it seems even harder, right? Yeah, maybe. Yeah. It's perfectly okay to just say anything, okay? This is why we like Rahul. Okay, right. So here's the completion of the story, right? If every component of H has no more than 2 edges, then you can do it in polynomial time, okay? Right? Okay. So now, I mean, in some sense, the story is complete, but if you're in a mathematics department, you have to make a living, you have to publish, and so what do? You look at special cases, yes? Right? So you look at special cases of the general problem. For example, you look at what happens if G is regular. Regular meaning every vertex has the same degree, and perhaps H is a small path like P4 or P3, just a path of length 2 or whatever, right? If you're in a computer science department, then maybe you look at approximation techniques, right? You look at approximation algorithms. If you're an engineer, then you try to do some optimization. You try to fit in as many of those as possible. Right, so I was in a mathematics department, and so we look at special cases where the graph G is special, regular, and H is a small path. The other interesting thing that we have tried to do is often the results are known of where G is a simple graph, so at most one edge between pairs of vertices. We have tried to extend some of those results to situations where there are multiple edges, several possible edges between pairs of vertices. Okay, so by the way, during the talk you can keep this grand conjecture of Ron Graham and Roland. It's Hayquist. So I asked somebody from his country how it's pronounced, and it's Hayquist. Okay. Every tree on n edges, draw me any tree on n edges, it will decompose every 2n regular graph. So, of course, the divisibility condition is trivially true, but there is the grand conjecture in the background of my talk. Okay, now here is something that you can assign your undergraduate students, actually. Yeah. So P3, the path on 2 vertices, decomposes a connected graph G. Of course, the graph has to have an even number of edges, right? P3 has 2 edges. But as soon as you have even number of edges, the path on 2 edges will decompose G. Yeah, not bad. It's nice inductive proof that you can actually give. So simple enough, huh? But now let's go to multiple edges. Yes. Okay. So here is a graph with possible multiple edges, and how many edges? 4, 5, 6, 7. Hang on. 3, 4, 5, 6, 7, 8, yeah, divisible by 2, right? Yeah, but have a go at it quickly. If the A goes with H, then the G has to go with F, and then E has to go with C, and you're stuck with the D, for instance. Yes? Right? Correct? Hello? Is it clear that P3 will not decompose that graph? Yes? Okay, so you cannot allow cycles of length 2. Yeah, path is a path on 3 vertices. Okay, so here is the model then. So what has been called as the line graph, one of the earlier speakers mentioned it. For each edge you put a vertex. So for A, B, C, D, all those guys, there are vertices. And if 2 edges share a common vertex, then you put an edge between those 2 vertices in the graph that you construct. So for instance, A and H share a vertex, and there's an edge between A and H in the graph below. Yeah? Okay. You don't put an edge between A and B. So, you know, those multiple guys you don't connect by edges. Now, here's another test problem at an undergraduate level, yeah? That P3 decomposes a multigraph if and only if the line graph contains a perfect matching, yeah? It's simple enough. If you think about it just for a few minutes, you'll see it's just translating directly, essentially. But now, so if I give you a multigraph, what am I saying? To check if P3 decomposes a multigraph, what do I have to do? I have to check if the line graph has a perfect matching, yeah? So now you're into general matchings, if you like, and you can use, there's a thing called Touch theorem, which says, you know, a graph has a perfect matching if and only if some condition. Huh? And you could translate that into this situation. By the way, you can check if a graph has a perfect matching in polynomial time. Extremely non-trivial algorithm, but it can be done in polynomial time. And so what's the story here? Going from a simple graph to a multigraph changes the complexity of the graph from an undergraduate little exercise to a very non-trivial algorithm. Yeah? Okay. So the problem increases in complexity tremendously by simply going from single edges to multiple edges. Okay. So one should be very careful when you go to multigraphs instead of just simple graphs in general. Right, so now I want to look at P4 decompositions of just regular graphs. Now, what if a graph is too regular? What's too regular? Every vertex has degree 2 cycles. And how are you going to decompose cycles into paths of length 2? Well, if the number of edges in the cycle is divisible by 2, then you'd be able to do it, right? Unless it's K3, the 3 cycle, of course, every vertex has degree 2, but you cannot decompose it into paths of length 2. So that's just a trivial observation. Now, okay, now here is another thing that you can use perhaps in a graduate level class. What if it's 3 regular? So all the degrees are 3, yes? When will P4 decompose a 3 regular graph? So Boucher and Fouquet, that's perhaps how you pronounce it. So a friend of mine, whenever he can't pronounce a name, he says, these fine gentlemen proved that. Okay, so all right. These fine gentlemen proved that P4 decomposes a cubic graph if and only if it contains a perfect matching. Yeah? So what about that example on the first page that I had? Do you want to go back to that? Yeah, let's see. That's a cubic graph, right? And it surely has a perfect matching. How about just the middle 3 edges? They form a perfect matching. Tell me what remains if you remove that perfect matching. Everything will have degree 2, right? But you orient these 2 cycles in a certain direction, and then what happens? At every vertex, after removing the matching, there's 1 in edge and 1 out edge. So the edges of the perfect matching can be used as center edges of the P4s. Yeah? And then what do? You use the 2 out edges at the 2 ends of the center edge. Yeah? Okay, so there. Let's go back. But that works in general. Huh? The center edges of the P4s form a perfect matching. Okay, so you go from 3 to 4 regular, and Heinrich and company proved that P4 decomposes a connected 4 regular. So you got to have the number of edges divisible by 3. And if it's connected and 4 regular, then P4 will always decompose a 4 regular graph. And the proof technique is by what are called triangle-free Euler tours. Okay, so there are 2 proof techniques that I have used. One is this triangle-free Euler tours, and the second one I won't have much time to discuss it fully. But let's look at what's going on. So Listen, an Euler tour is one which starts at a vertex in a graph, goes through all the edges exactly once, and returns to the starting point. Right? Okay. And standard theorem, perhaps the second theorem in graph theory class, is that a connected graph has an Euler tour if and only if all the degrees are even. Yeah? Okay. Now, a triangle-free Euler tour is one where no three consecutive edges in the tour form a triangle, all right? Including the wraparound, okay? So here is an example. So let me see. Now again, even this is, the colors are light and I have a problem with it. But do you see the wraparound? E-A-C-E, right? Yeah? When you come back, even that's a triangle, right? And you can't have that either, okay? Not just in the middle, but when you wrap around, you cannot have a triangle. So no three, if you look at this as like listed in a circle, right? Yeah. And no three consecutive edges of the Euler tour can have a triangle. Right, so in this graph, here, you know, there's several reasons why it's, well, at least two reasons why it's not triangle-free. But it's an Euler tour, and an Euler tour is triangle-free if such a thing doesn't happen. And, well, you can verify that there's an Euler tour with, which is triangle-free. Hey, tell me, what use would a triangle-free Euler tour be? If you wanted to find a P4 decomposition, it would be fantastic to have a triangle-free Euler tour. What do? You just start chasing the tour and pick three edges at a time, yeah? That's going to give you a P4 decomposition. So it's a stronger property than a P4 decomposition, but you know, useful. All right, so a couple of things. Two-factor has been mentioned, just a collection of cycles that hit every vertex. Here's this Peterson's theorem that sometimes is useful. Every even regular multigraph has a two-factor. Yeah? Okay, so you give me a 10 regular graph and I can start extracting two factors out of it. Okay, okay, so here is a theorem of Heinrich and company. A 2-4 graph is where all the degrees are 2s and 4s, nothing else, all right? A connected 2-4 graph has a triangle-free Euler tour if and only if it's not one of the ones that I have drawn there, okay? So, you know, you can check that any, by the way, what's H? H is some other graph such that the degrees are 2s and 4s, yeah? Okay. As long as you have these substructures, you're never going to find a triangle-free Euler tour. So what about if the graph is 4 regular? Then what are the problem cases? Well, those first 4 don't come in, right? They do not come in if it's 4 regular. These last 2 are problem cases, yeah? Okay. So using this, by the way, Ajit at IIT Bombay has obtained a much cleaner proof of this. Anyway, so I thought I should mention that. Right, so then using this theorem, they derive as a corollary that if you have a 4 regular graph, I mean, look, it doesn't necessarily have a triangle-free Euler tour, but you can use the fact that unless those structures are there, it has one to prove decomposition into paths of length, of edge length 3. Right? Yeah, so because of the wrap around, you try it. You go outside, then you go inside. Yeah, when you wrap around, okay, yeah. To write it out, you'll see it. Yeah? Okay, it doesn't. Yeah? So when you come back, remember I said there will be a triangle. Yeah? Okay. So now, here is the killer, right? Here is the killer. Every 2k regular graph, for k at least 3, 6 regular, 8 regular, blah, 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 guaranteed to have a triangle-free Euler tour. Yeah? So it's a theorem of oxymates. a PhD thesis with Hayquist being her advisor, yeah? It's 47 pages of unreadable stuff. I'll show you a typical page from her thesis. Case by case by case by case, and I don't know how many times I have to say that, but you know, things where you start reading, you get no intuition into anything, yeah? At least I don't. All right. So, I mean, a corollary of her thing is that if the number of edges is divisible by 3, then you're going to get a P4 decomposition, right? Yep. Okay. Of a 2K regular graph for all k greater than or equal to 3. Now, we have been trying to extend results on simple graphs to graphs with more edges, and we had a different approach to these things, and it is just not working well, okay? So we decided we would look at the triangle-free Euler tors, and in order to really understand something, we said we are not going to look at her result and we'll try to independently derive it, yeah? This is usually the best way of understanding something, is to independently try and derive something which is known already, I think. For at least some time, then you really understand the difficulty of it. So the current work, which is not published yet, has that as the motivation to really try to understand what's going on in a result or try to derive it differently. Right, so that's that. Now, before I do that, so, you know, that settles the thing for all even regular graphs, yes? Right? Correct? P4 decomposition of even regular graphs is completely settled by her result. And then what about odd regular? Well, before I go to that, let me show you a typical page of her. This is a typical page of her thesis. Okay, it's hieroglyphics, right? I'm retired, surely I don't have the patience to read that. But perhaps a graduate student can be assigned to go through all the details. And the only reason I believe it is because her advisor is a famous man. Yeah? Okay. So what happened is it never got published. Nobody is going to publish this kind of stuff. Yeah? Okay. But you know, I believe it because of Hayquist being her advisor. So that's that. Right, so here was one of our results that it is NP-complete to determine if P4 decomposes a 5 regular, okay? So you go from 4 to 5 and the problem becomes impossible. I won't even talk about the reductions, but these are pretty reductions, very nice, tricky things. As you know, finding these reductions is not easy. And there are some very nice reductions, but I won't go over them. In general, checking if P4 decomposes any odd regular graph is hard. Okay? So that's another one of our results. Yeah, again. Okay, so now let's move on to multiple edges. Yeah? Okay, because it completes the story, right? You know, all the odd ones we proved are NP-complete. The even ones, Oximet's result covers that. Although we don't fully understand our result, but that's ongoing work. Right, so if you go to a 3 regular graph and you possibly have multiple edges, then remember, for a simple graph, what was the condition? That there be a perfect matching, yes? Right? I mean, the one on the left does not have a perfect matching. And so, although the number of edges, 15, still divisible by 3, but doesn't have a perfect matching, will not decompose into P4s. Here, the number of edges is divisible by 3, and it does have a perfect matching, actually. The graph does have a perfect matching. Yeah? But what you need is you need a perfect matching consisting of single edges. Again, you can have students prove something like that, that if you have multiple edges and it's cubic, cubic meaning everything is degree 3, then the condition changes to having a perfect matching with single edges. What time did I start? What time did I start? 15 more minutes? Yeah, okay. Right, so here's a theorem which extends that 4 regular result of Heinrich and company, yes? So if the mu of g is the multiplicity of the graph, largest number of parallel edges. So if you allow some singles and some doubles, there is a triangle free Euler tour and plus also note cycles of length 2 in the Euler tour, okay? If and only if G is neither one of these structures, yeah? Okay. And as a corollary of that, I won't even try to go over the proof here, is that if you have a 4 regular graph with multiplicity no more than 2 parallel edges between vertices, unless you have this structure where if you look at any 3 vertices in the graph, you can't have more than 4 edges there, okay? So for example, I mean, if I have something like this here are 3 vertices with 5 edges there, and you can see it's going to be a problem, right? So I take that into one thing, I take that into one P4 and one into P4 there, and then I'm going to have a trouble with the rest of the edges there. Huh? So, but the theorem says that unless I have that, then it will decompose into paths of length 3 or P4s. Right, so, okay. Now, here's another one, Bondi, okay. So you take a cubic graph, unless it may not have a 1 factor, and then of course you cannot decompose it into P4s. But if you double every edge, G2 is the graph of 10, by just doubling every edge of G, then yes, yeah? Double every edge of your cubic graph, then P4 will decompose what you get, yeah? And, you know, our proof was this other technique that we have been using at choosing a special type of 2-factor and so on, and I cannot get into it. But here was the biggie. Here, this was an important and difficult paper, which is a generalization of Bondi's result. So Bondi says you take a cubic graph, double every edge, and P4 will decompose it. Now I'm saying take any 6 regular graph with double and single edges, possibly, right? So some double edges, some single edges. And P4 will decompose every such multigraph, yeah? Okay. So this was a difficult one to prove. It is a paper with El Zanati, Mike, and myself. You know, in all these things, you want to know where is the boundary of what you can do, right? Yeah, so you go multiplicity 2. What happens if I have 3 edges between pairs of vertices, yeah? And there, it becomes NP complete at that point. So I think this is how a lot of this research should go. You try to push it as much as you can, and when, you know, the time it is essentially sort of settled is when you say, okay, now it becomes hard, right? And you prove it, okay? So for multiplicity, possible multiplicity 3, the problem is NP complete. In fact, you can generalize both those results to 6K regular with multiplicity less than or equal to 2K being okay, and with multiplicity 2K plus 1 being hard, yeah? Okay, so 2K is where the boundary of what you can know is. Okay, okay, so, you know, there are some open questions about this, and I remember trying to look at some special cases. These are all questions about when there are multiple edges, what happens. And even small cases are completely open. So for instance, you could take this conjecture and stick in k equals 3, and it's open. Okay, so 6 regular with multiplicity, what is it, k equals 3, less than or equal to 3, so possible multiplicity 3, and no 3 vertices inducing any more than 6 edges, prove that P4 decomposes G, of course, if the necessary condition is satisfied, which being that the number of edges is divisible by 3. I won't go through any evidence. We have evidence about the conjecture. It's not just blind. There is evidence that possibly the conjecture is true, but I cannot have time to talk. I don't have time to talk about it. So, okay. So I want to say a few things about the ongoing work which I'm supposed to be completing, right? Yeah? Okay. So this is about what I call low density halvings. Okay, halving of a graph or a multigraph, you have to partition the edges of G into 2 pieces such that the degree at each vertex gets halved. Okay? All right. So tell me, do you agree with this, that a connected graph has a halving if and only if all the degrees are even? Yes? What do? You take an Euler tour and just place edges alternately in G1 and G2, right? Yeah? So in any case, there is the definition of a halving. Now, the question is, I take a connected 2K regular graph with an even number of edges. It has to have an even number of edges, huh? Right? Yeah? Because you could have 2 disjoint K3s. Sure, all the degrees are even, but you cannot have it, right? You cannot have a K3. I mean, right. So connected 2K regular graph with an even number of edges. Okay, you can have it, but I want the 2 halves to not be too dense. Okay, whatever that might mean. Yeah. Okay, and let's try to clarify that. So neither half should contain a dense subgraph. Okay, for example, k equals 2. What am I saying? Take a 4 regular graph, split it into what will happen? Two regulars, yes? What? Just a bunch of cycles. Yeah? Spanning cycles, hitting every vertex. I do not want either of the pieces to contain a triangle. Simple question. Take a 4 regular graph, split it into two regulars with neither piece containing a triangle. Not always. You cannot do it always, but amazingly, there is a polynomial time algorithm to check if this is possible. Okay, and I wrote to Horak, and I asked him, do you know of some structural characterization of this, right? That you can split it into two regulars without a triangle if and only if some obstructions, yes? Some kind of obstructions in the graph G. And he said he doesn't know, and it's been a long time, and blah, blah, blah. So there is something to think about. Can you characterize structurally? I mean, this is an odd kind of thing to ask. If you're a computer scientist, having a polynomial time algorithm is the end of it. I mean, that's as good as it gets, right? Who cares about the structural? Some people do. Okay, suppose I go from 4 to 6 regular, yeah? I'm going to show you that you can actually have this, yeah? With neither piece containing a K4, yeah? All right, right? So that's sort of the next step. And if I left this diagram on the board for about 15 minutes, some of you might figure it out, but let me, yeah, 5 minutes, okay. Should I walk you through it? 5 minutes, difficult. Maybe I come back, maybe I just tell you the important thing, the results, you know. In any case, in general, you can show that if you have a 2K regular graph, then you can split it into two pieces, two halves, such that neither piece contains a k plus 1. That's what I mean by not too dense, yeah? Okay. So those complete graphs, I'm calling them dense. Can we do better? Well, you know, so take a 6 regular. Can you avoid a k4 minus an edge in the two pieces? I don't know. This thing, you know, the theorem on the top surely implies that you can avoid k5. But can you avoid a k5 minus an edge? And this is completely useful. Why is it useful? Remember that theorem about triangle-free Euler tors of Heinrich. If the 4 regular graph is devoid of k5 minus an edge, then there's a triangle-free Euler tor, yeah? So what can I do with an 8 regular graph? I can split it into 2 4 regulars, if I can, without k5 minus an edge, find an Euler, triangle-free Euler tor or triangle-free Euler tor here, and then there's a problem of gluing the 2 Euler tors together, thus obtaining a triangle-free Euler tor of the 8 regular big graph, yeah? Once you get a triangle-free Euler tor of an 8 regular graph, then you can decompose it into P4s, okay? So, turns out this is what I have to write up anyway. Calling it a theorem. It will be a theorem. 8 regular graph can be halved into 2 pieces, neither half containing k5 minus an edge. And then the gluing also works, yeah? So you can glue the 2 Euler tors, triangle-free Euler tors, to get a bigger triangle-free Euler tor for the entire graph. And more generally, you can do this with a 4K regular graph, k at least 2, yeah? So 8, all multiples of 4, right? 8, 12, blah, 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 yeah? Okay. So tell me what that does. It obtains a proof of Oximet's result for multiples of 4. She proved it for all even regular graphs, and we have it for multiples of 4. We understand it more clearly than I showed you that page from the thesis, right? But some gaps, 6 regular, if we can understand that, then it completely fills up the whole thing. But look, I mean, here's my general question. It has led to a general question. I have an even regular graph. Splitting the even regular graph into 2 pieces where the pieces don't have dense pieces, yeah? No dense subgraphs in the 2 pieces. So that's a completely independent question anyway, right? Yeah. Having a graph into 2 pieces, having an even regular graph into 2 pieces with neither half containing a dense subgraph. I should stop on time, flights will leave and so on. Thank you very much. Yeah, some kind of complete subgraph or some kind of complete subgraph minus an edge if you can avoid, as good as you can do, right? As good as you can do. So, for example, you know, I can prove that if you have a 6 regular graph, then you can have it without either piece containing a k4. But you can try to do better. Can you avoid k4 minus an edge?
Suppose if your graph is regularity is high enough, say for example 20,
Yeah.
then whether you can ask for as a k5 or k6, something like that.
Yeah.
But you don't want to have a k9 or k10.
Oh, yeah. I mean, as a subgraph, so if the bigger one's there, then the smaller one's there
so-
too, right?
Yeah.
So as good as you can do is my question, right?
So
And so that's what I mean by no dense pieces. So the thing is, I wanted to use that Heinrich result, right? Which said that if there is no k5 minus an edge in a 4 regular graph, then there's a triangle-free Euler tour. Yeah. Okay. So avoiding things that are very close to complete graphs. Yeah. Of the best size you can. Right. So for 6 regular, I can actually prove that you can avoid K4s. But then if you like, side question would be, can you do any better? Yeah. K4 minus and edge. Not that I know of any practical implication of that. For the K5 minus an edge, it was motivated by P4 decompositions. Yes. But then it has become a question of its own, right? Yeah.
But if the graph is too dense itself, for example, if you take A2n plus 1, then if you want to decompose like that, then eventually you may get large
so
subgraphs
the thing that we could prove is that if it's 2k regular, right, then you can avoid a k plus 1. Yeah? Yeah. That's what. So the proof I was going to show you for 6 regular avoiding a k4 would have illustrated the proof for the general case for a 2k regular avoiding a complete k plus 1. Okay. Now, can you do better than that? That's open. Rahul, no, come on, no questions from you. Okay, well, what? I'm just kidding. Yeah. Okay.
Many edges going across.
Okay.
It's an NP-hard problem, but there's a 2-factor approximation algorithm.
Okay.
So if there is 2k, then there is an algorithm which guarantees at least k of the edges of every vertex, and that kind of algorithm gets towards it.
So I won't pretend to know much about what he's saying, but I will tell you that a lot of these things are known for asymptotically. Okay. So for instance, the Graham-Hequist conjecture that every tree on n edges will decompose a 2n regular graph is known if n is bigger than the number of atoms in the universe. Yeah? Things like that. Yeah? So the bounds are crazy like that, huge. If n is at least 2 to the power 5,000, then these things, a lot of these things are known to be true. And like Rahul says, there are some approximation methods for certain things. I don't know exactly how they apply here, but yeah, so we'll talk more about it after this. Yes. Well, okay. So my experience with these things usually is that all these nice, clean techniques usually don't apply to open problems. Okay, I'm making a wild statement, right? So I think that the questions in graph theory that have been open for a long, long time. Yeah. Okay. So, for instance, there is the Seymour-Goldberg conjecture, which extends results in edge coloring of simple graphs to multiple graphs. And you can formulate all these things in terms of matrices, linear programs, integer programs. But, the actual use of these techniques, I don't know how far it goes. Okay. So, I'm sure people try these things. And when you find use of algebraic techniques to prove theorems in graph theory, it's a beautiful thing. I think it's an absolutely beautiful thing. But those kind of flowers are rare, I think, especially with respect to unsolved problems that tend to be messy things. That's a personal opinion. Sorry.
I request Dikvija to felicitate Dr. Tipnis.
Thank you very much.
Our next speaker is Dr. S. Francis Raj. He is an assistant professor at Department of Mathematics, Ramanujan School of Mathematics, Mathematical Sciences, Pondicherry University, Pondicherry. I would like to request Dr. Francis Raj to deliver his invited talk on interpolation theorems in graph coloring.